All right, well, now I'm going to introduce Maurice Doucet, and Mo is the Chief of Software Research at Quality Positioning Systems. It's formerly from IVS 3D, so you may be familiar with the product Fledermaus. It's been around for many, many years in the mapping and visualization and analysis aspect of ocean mapping and ocean data management. And Mo joined the company several years ago now and has helped in advancing some of the newer technologies, especially in midwater column mapping and some of the breaking stuff that he's going to share with us today. QPS is actually a business partner of Esri. We've worked with them quite a bit, and we've actually developed some workflows that go end-to-end as far as the full spectrum of processing of hydrographic data. So, Mo, I'll turn it over to you and look forward to your presentation.
Thanks, Tim. First, thanks to Don and Esri for inviting us to come and speak. It's always nice when we can come and speak with colleagues in the ocean domain. I'm going to try to ram through this fairly fast because I've got a lot of slides, but this is basically our background, founded in '95 out of the Ocean Mapping Group at UNB. Our real focus was 4D visualization for ocean mapping, hydrographic survey, and earth sciences. We started the integration with ArcGIS technology in 2009. We merged with QPS in 2011. We have offices in the Netherlands, US, UK, and Canada. So, historical perspective, this is how folks used to get bathymetric information. You know, you had the guy dropping the lead line, you had someone driving a boat, and these guys were probably shielding the beer cooler. But that's what it was. Data volumes, lead line, this is what we're having to deal with. The interesting note is the megabytes per hour. So first, second, third gen sonar, not too bad. Modern sonars like the EM 2040 dual head, we're talking 144 million soundings per hour and about 4 gigabytes of data. When you tack water column onto that, you're up to around 150 gigabytes per hour. And these guys are running 12 hours for weeks on end doing surveys. So we have to deal with those kind of data volumes and reduce it to something that the scientist can end up using. So what are we dealing with? Obviously, ship, water, some kind of seabed. The desired bathymetry and backscatter that they're looking for, it could be mud, sand, gravel, rock. The composition is important because that informs the habitat, and habitat is an important part of a lot of different types of ocean science. In the water column, you have biomass, you have some geophysical processes, thermal vents, bubbles, and you have unknown hazards from wreck, masts, snag nets, things like that. Now, in that water column is the thermal gradient. So when we're doing survey operations, you have a sound pulse that travels through the water column, and because of the thermal gradient, it doesn't travel in a straight line. But with the magic of physics and a little bit of math, we can find out where those beams actually interact with the seabed. So this is a view of a swath of data. The bottom track is basically what the determined location of the seabed was for a particular beam of the swath. And from that, obviously, we'll get a cross track, which is a cross track from the vessel, and a long track, and a depth. And that's where we get our hydrography. Now, with newer sonars, we're getting something called footprint time series data. So where each beam of the data interacts with the seabed, you get a footprint. And inside that footprint is a time series of information, all coming from the same echo. That time series is a set of intensities, amplitudes, based on the composition, the reflectivity of the seabed, and that can give you the image of what the seabed looks like. And that's what, this is a typical waterfall of seabed. Now, when we bring it into the 3D environment, this is where it starts to look really interesting. This is Lake Windermere in the UK. It's a 2-lobe glacial lake, and this is done with a EM 3002 sonar. But from the bathymetry, you get a good view of some of the processes going on. There's a slide that happened up here, and this is what folks typically dealt with, just the bathymetry. But now when you add the backscatter on that, all of a sudden you see there's a lot more information. So there's signs of where they were moving some sand around. There's some dredging and dumping that was going on here, probably some anchor scarring here, but lots more information that's provided to the hydrographer. Now we go back to our water column with the newer sonars, is while the beam is traveling through the water column, we can also get a water column time series. Now this data was always present. This is where sonars, they would use this data to determine what the bottom, where the bottom actually happened. But then somebody said, hey, there's all this additional information in here that might be interesting because it's interacting with biomass and other processes as it's traveling through the water column. This is a view from our water column tool. It's an oblique view, so a long track is going left to right. And what we've done is we've taken all the beams, all the time series information, collapsed them down and stacked them. And what you can see is there's lots of things happening in the water column. There's fish. This is probably some plankton. And of course right here we've got a wreck. So when you put those together, this was a wreck surveyed during the New Zealand Shallow Survey 2012. So this is the typical bathymetry. You add on the backscatter, more information, and then you add the water column, and now you see the detail of the wreck. So bringing all the different modalities together, you get a much better picture of what's happening in the ocean. Now, general data processing, I'll buzz through this because it's very dry. But bathymetry, what we do is we have interactive 3D visualization. There's some statistical surface estimation because what a hydrographer wants, he wants the best estimated surface. There's an algorithm that we use called Cube that was developed at the Center for Coastal Ocean Management at UNH that does this. And even after the statistical algorithms run, there still might need to be some human interaction to do some area-based editing. So it's kind of an iterative process. When you're in Fledermaus, you'll see all these spikes that were left out after the algorithm. So the user can bring that into a 3D editor and just select points and reject them. So this is how they can interactively clean up the bathymetry. For backscatter, lots of things have to happen with backscatter. Our processing, we have to correct for receive gain, transmit power, the pulse width, spherical spreading, water column attenuation, all of this list of things that happen as the sound wave travels through the water column. So this is an uncorrected view of backscatter of a survey, and then once all the corrections are applied, it turns this ugly mess into that. So you can get a much better view of what the seabed looks like. Now for water column is more, at least right now, it's more of a feature extraction operation. We do some signal processing to transfer the amplitude to volume backscatter or power, or simple power, or target strength. But really what we want to do is we want to threshold out background noise, we want to potentially threshold out beams, focus in on an area and depth range, and then export that data as visual metaphors to Fledermaus so you can do some analysis and then before pushing it into ARC. So this is just an example of some of the GUI. So you're doing some beam limiting, some range limiting, and then some histogram limiting. And then what you get out of that is when you export to a 4D environment is we have different metaphors to look at the data because in the water column you can have artificial distortions just due to the swath, how the swath travels through the water column. So this is what we call a beam curtain. So a lot of us were talking yesterday about one of the needs for ARC to handle profiles. But in this case, it's not just a simple vertical curtain, it's a curtain that's aligned to the beam. So it's bent according to what the aspect of the beam was. And in this you can easily see these were fish traps in Portsmouth, New Hampshire that the sonar was traveling over. And then the fan time series, so you get the full swath. We can bring that into the 4D environment so that the user can add that to their visualization. It does have high distortion at range because as your beam moves away from the sonar head, it's going to spread. And point clouds, obviously, when you've done your thresholding, you can export out those point clouds. This is the multi-beam sonar picked up the fish traps and all the mooring lines that were attached between them. all the attributions can carry as well when you export that data out. And of course, volumes. We generate axial surfaces. You can export them at variable resolutions, so you can see the internal composition of a process. This was a plume, a 1,400 meter plume that was discovered off the Mendocino Ridge during the shakedown of the Okeanos Explorer. They just accidentally drove over it, and the guy on watch at 4 in the morning happened to turn the water column recording capability on in time to catch this. And it caused a lot of buzz, made some local NOAA news, and immediately scientists were like, what's going on, what's happening? And they subsequently had a mission back to see if it was still there. And not only was it still there, but there were seeps, hydrate seeps, all over that ridge. So that's what we do for the data processing and analysis. So during our phase 1 integration, what we wanted to do is we wanted to give our user community, and this was also a request from our user community, because they were having to start to deliver product in an ARC geodatabase. So they're doing all this processing and visualization in FleeterMouse, but the end product that they needed to deliver to the customer needed to be in a geodatabase. So what we wanted to do is we wanted to give them a seamless experience and try to make it so that it was felt like they were working in the same environment as ARC. So, sorry about that. The way FleeterMouse works is FleeterMouse has a scene, a notion of a scene. In it are objects, SD objects, and one of the objects that we added that you could create was an ArcGIS workspace. So that connection to a database just becomes a part of the scene. And you can have one connection, many connections, and what it allows you is it allows you to move data back and forth between ARC and a geodatabase. So this is just an example of one of our attribute panels for a DTM or a surface. So you could transfer the survey area, which is the polygon. You could transfer the bathymetric raster or the image raster. And this is the connection, the view in the attribute panel of your connection. So you see the ARC objects just as you would if you were viewing it in ARC catalog. This is the export panels. So if you have multiple connections, you pick the connection you want to export. You can do some transformation on the way in, or excuse me, on the way out to ARC. And you can decide where it's going to go, if you're going to put it in a feature data set or which database you're going to go into. Now coming back the other way, all you do is if you have your ARC connection, you just right click on one of the feature class or a raster, and you just say load to scene. If it has attribution, you can do that attribution mapping to the FleeterMouse SD object, the scene object, and you can decide not to bring those attributes in. It's your choice. And this is just a view of, so here we have a FleeterMouse scene of what we call a PFM, which is the hydrographic surface along with all of the underlying point data. And these are just the exported components out. You have your survey area as a polygon, you have your bathymetric raster, and you have your image, your hill shaded, FleeterMouse's hill shaded version of the surface. These are water column points, just exported as XYZ with attributes in time. So, you know, they're in a feature class in ARC with that with those attributes. So when time gets, you know, better use, we can use that. This is just simple polygons. So we do some interpretation in FleeterMouse. So you can export polylines, polygons. You can have subtypes, so you can carry through interpretation back and forth between the ArcGIS environment and FleeterMouse. And then here's another view of the PFM. So here we have additionally plotted soundings. So when we run our sounding selection algorithm, which is basically takes all that high resolution hydrographic sounding data and reduces it to a set of points that are going to be used to put on a chart. And that's where they end up. So the second phase of the integration, which we're in now, we're trying to move a little closer to working with the maritime team. And what we have in our customer, you know, kind of cross section is we have people that we call FleeterMouse centric folks, and we have folks that we call ARC centric folks. So the Fledermaus guys know and use Fledermaus. It's kind of what we discussed yesterday, where people kind of like to use the tools they're used to. And what we did is those folks were starting to have to deal with ARC, so we made it simple for them to move their data into ARC without having to learn too many new things. Now we're kind of flipping it the other way. We have ARC-centric folks that are starting to move into the hydrographic world, so we want them to get their feet wet with some of the capabilities that we have in Fledermaus. So what we're developing is a set of geoprocessing tools that'll be part of the maritime delivery and mainly around the BIS. So easy ways to move data, bag data back and forth, and also Fledermaus types, and then some specific functionality dealing with sounding selections. Where we're going, more GP tools, obviously. This has been an obvious place for us to fit. We have a lot of processing, and as we bring more of the ArcGIS-centric users into our community, GP tools are a really easy way to get those folks to use the processing capabilities that we have in Fledermaus. ArcGIS extensions, so as our breakout group discussed yesterday, Arc can't do everything, but one of the great things that it does do is it's really extensible. So with ArcGIS extensions, we can get to do some more Fledermaus-y things, but do them in the Arc environment. And then whatever our users are requesting. So we're starting to get more folks that are doing GIS and doing hydrographic work in Fledermaus, and the user community is a big push for us. I just wanted to end on if it plays, an eye candy. So this is just an output from a Fledermaus scene. So this was that fish traps data I was talking about. Here we're dealing with 4D information. Visualizing the swath, visualizing the beam curtain, visualizing the points as they're acquired. And then this is just another view of the 1400 meter plume. Again, isosurface, but multiple isosurfaces. So the surface is generated at multiple resolutions. Sorry about that. I wanted to point instead. See if it'll. No, it won't.